Ladies and gentlemen, let me welcome you here. I'm here to chair this session, so I'm doing this. We have a little delay because of some technical issues, but don't worry, all speakers will have 20 minutes time slot. So the first speaker of this session in Jan Livens. I hope that my pronunciation of your surname is correct. And the title is Operations on Fuzzy Variables with Constraint-Based Interactivity. Please take the floor.
Well, hello everyone. My name is Jan Levens. I'm a PhD student at Kermit at Ghent University, and today I will be presenting some joint research by me and Bernard Batz. For that, let me start by introducing compositional data. So compositional data is when you have multiple quantities that are part of one whole. In particular, that means that these quantities will also be related. Because they are bounded, well, in total by the sum. Let me give a small example. We've all had the coffee break. There were some fruits there. So we can do this example. Have a number of apples, a quantity A apples. We have O oranges, and we have F total fruits. Then naturally, these three are linked. Here, the compositional data, the apples plus the number of oranges, will be the total number of fruits. And conversely, we can also derive the number of oranges by and the number of apples if we know two of the three quantities. So naturally, we can expect these quantities to not only be crisp, but also be fuzzy quantities. Firstly, we can represent them using fuzzy sets. So if you look at these subtractions, this will be subtraction of fuzzy sets. For that, we have the following question. If we have two fuzzy sets, A and B, what is their difference? Well, there is a very natural way to do this, to look at this, and we can do that by using the Zade extension principle, which generalizes or like extends the function of real numbers to a function of fuzzy sets. Exactly. Well, we can look at all options to reach a certain value by the function, and then we have to take the supremum of the possibility of all these options. Okay. If we apply that to our example of the difference of two real numbers, that means our origin space will be R2, couples of real numbers. We will go to one single real number, which will be R, and the function is, of course, a subtraction. If we plug that into the formula, we get the following. So this is just the Zade extension principle applied to the difference of fuzzy sets, where we, of course, look at all the options such that the differences match. This works well, except there's one remark I want to make. If it's not a singleton, we don't reach the zero set or the zero function, the characteristic of the singleton zero. It might surprise you because there is one intuition that if we have some number, like some quantity, and we subtract itself from it, we expect to reach zero. Now this observation has been made before by multiple others, and some have implemented like a new way of subtracting fuzzy sets to get this desired result. As well, one of them I will go into great detail, which is the generalized Ruakara difference, which tries to solve this issue by getting quite explicit in inverting the addition. So how does it define? Let A and B be compact fuzzy sets, and we will define the difference of A and B certain fuzzy set C, such that either A is the sum of B plus C, or B is A plus minus C. In this way, we have like the intuition here is, of course, that this is explicitly inverting the addition, and that yields the following results. So first of all, I need to mention that this difference isn't always defined. This construction of these two conditions on the right is as there is at most one solution, but that doesn't guarantee there's always one. But what we do have is that the generalized Huakara subtraction of a fuzzy set with itself will actually be 0. So that's a good step. We have solved the issue we are looking for. For the next part, I need to briefly introduce fuzzy intervals. A fuzzy interval is a special type of fuzzy set, namely a fuzzy set for which the alpha cuts are non-empty, bounded, and closed real intervals. And what this means, of course, because the alpha cuts are closed intervals, we can characterize them, well, we can associate two endpoint functions to our fuzzy interval as follows. Well, the endpoint functions will be the left and the right side of these intervals. This is a special class of fuzzy sets. Is quite interesting. Why? Because it has a special role in fuzzy modeling, because it's naturally very well equipped to represent physical quantities, which are often the membership functions are often convex. And the alpha cuts are non-empty, bound, and closed, but in particular, it also has these nice mathematical properties, namely the fuzzy set itself will be normal, will be quasi-convex, and upper semi-continuous. Now, for fuzzy intervals, we can get a second characterization of this generalized Huakara difference. Well, we can express the generalized Huakara difference in terms of the alpha sets by using these endpoint functions. So that's given by that formula. In particular, because we now have an explicit formula that only works for fuzzy intervals, that means that if A and B are fuzzy intervals, we also know that the generalized Huakara difference of them always exists. And of course, we still have our desired property, namely the difference of A and A will be 0. So that leads us to the question, have we solved it? And if we did, the talk would already be over, which isn't the case. Well, there's a few remarks I want to make. One of them, well, let's start with a few remarks. We've now defined subtraction as a kind of an explicit inverse to addition, but on the level of fuzzy sets. While the original subtraction was on the level of real numbers, now we have defined on the level of fuzzy sets, which yields to an ad hoc definition to solve the issue we noticed. And also, these formulas aren't generalizable to other functions. We can't expect to build these formulas or these definitions for every possible function. So these few remarks indicate there might be an issue in the way we're doing things. Another way to view this is with comparing them to normal real intervals, to crisp real intervals. If you do the Minkowski addition and Minkowski subtraction of normal real intervals, they also have this same property, namely that the difference of an interval with itself won't be 0 either. So keeping that in mind, it might be worth to look at this with a different toolbox, a different point of view. And so instead of using fuzzy sets, we might better be off using fuzzy variables. So what is a fuzzy variable? Well, for a fuzzy variable, we need a few things. First of all, we need a universe with events. Then a maxitive measure from this universe to 0, 1 in this case. And with those, we can define a real fuzzy interval variable or also a possibilistic variable, which will be a function from the universe to the real numbers, which is actually quite comparable to the concept of a random variable in probability theory, except that now we are doing it in a fuzzy setting. So likewise, a fuzzy variable will have a possibility distribution, which which is the push forward of the maxitive measure to our variable x. But in particular, that means that the possibility distribution at the real number x will be the possibility of the variable taking the variable. This yields a kind of a factorization of our total maxitive measure. We can express the total maxitive measure as factorized through our variable in our probability distribution of that variable. Okay, so now let's try this. Let's try applying fuzzy variables to our original question. And that leads to the following. So in this case, I will particularly use an interval fuzzy variable, which is a fuzzy variable of which the possibility distribution is a fuzzy interval. And we will try to look at the difference of the variable with itself. I put made it quite explicit a calculation here. Why is that? Not because that's mostly because to show you that there's no magic involved. It's all normal intuitive steps that leads us to the desired result. And one particular thing I want to point out is here that we have the possibility of combined events, a possibility of A be equal to Y, and also A equal to X plus Y. Of course, this means that these two things need to be the same, and hence X needs to be 0, which yields, in the end, the characteristic function of the singleton 0. So with fuzzy variables, we didn't at first need to define a different kind of subtraction. We actually directly get the desired result or the intuitive result. So with this in mind, let's test it on a more complicated problem. And that's the following problem statement. So we have two fuzzy, interval fuzzy variables, and want to find a fuzzy vector. In this case, a fuzzy vector will be a two-dimensional variable, such that the first marginal corresponds to one of our variables, and the sum of this vector will be the second. What does it mean? Well, it relates back to our initial problem of oranges and apples. Mainly, the sum will be the total number of fruits. One of the marginals will be the number of apples, and the other marginal will be the number of oranges. Now, for computational reasons, it's often easier to not work on these variables directly, but look at their possibility distributions, which is why I rephrase the whole problem statement in terms of fuzzy sets. In this case, they're not fuzzy interval variables, but they're fuzzy intervals. And we look at the fuzzy set over R2, which is, again, well, a two-dimensional fuzzy set, which satisfies the following system. So first of all, again, the sum needs to be equal to our A, which in the example is the total number of fruits. The first marginal needs to be B, which can be the number of oranges. And so that's the main part of the system. The third condition is more of a technical condition. We don't have time to explain exactly why it's there, but it's intuitively, we want the number of oranges to also be a physical quantity, which means why it makes sense to restrict it to only fuzzy intervals. And this system of equations or system of foundations, of course, it's a set of solutions which I would denote by S. Okay. About this system, there's a couple of cool or like interesting theorems. First of all, we can bound this set of solutions with an explicit upper bound for this set, which is given by that formula, which will be the gate element of our solution set, and also which second marginal will equal, or that second projection of this set will equal A minus B. We also have a lower bound given in a slightly different form, namely here again the generalized Huakara difference will be smaller than the second projection of every element in our solution set. So with these two bounds already quite interesting. I still have one nicer result, even a full characterization of the solution set. We can fully characterize at least the second projection of the solution set as all fuzzy intervals that lie between the generalized Huakara difference of A and B and the normal difference. So this is actually the full solution of the full characterization of the solution set, which in particular lets us do one interesting thing, an alternate characterization of subtraction. Because we have this full characterization of the solution set of our problem, we can actually view subtraction and generalized Huakara subtraction in a different way, mainly as the supremum and the infimum of the second projections of our solution set, which is, I find, quite interesting. Okay, now finally, as I also promised in the title, functional constraints. Let's look at functional constraints. So functional constraints are when one of the variables or both variables are bounded by a functional constraint. In this case, I will look at a simple constraint. B, the fuzzy variable B will be equal to f of A. And for this first example, we can look at the sum of these two variables. So if you look at the possibility distribution of these two variables, we get the following formula. The key of this condition on the right side will be the evaluation of this logical condition. So it will be either 0 or 1, whether this is true or false. But if we work that out further, we get the following idea where we can calculate the possibility distribution as the supremum over this set. Now, this set has a couple of, we try to understand the behavior of this set. And the behavior of this set is closely linked by the properties of the function identity plus f. Particularly, why is that so? Because we want to take the inverse of this function. So if identity plus f is injective, this inverse will yield at most one value. If it's surjective, it will lead at least one value. And if it's bijected, it will be exactly one. So we can look at some classes of functions that yield these results. Mainly, identity plus f will be injective if f is, for example, strictly one Lipschitz continuous, or if f is strongly monotone. These are, of course, not the only classes of functions that yield this result, but they are interesting classes. Conversely, on the other side, we have surjective. If f is strictly one Lipschitz continuous or a maximal monotone linear operator, identity plus f will also surjective. So in particular, the strictly one Lipschitz continuous functions are an interesting class because then it means that identity plus f will be bijective, which yields the most regular behavior of our thing. Yes. Finally, I want to do this on general functions. So instead of addition on general function g, which yields the following expression. In this case, we haven't found any clear classes or clear characterization on when this function will be injected or surjected. That may be part of future work, as well as we have also looked at inequality constraints, that of equality, of slightly different forms of equality, and even fuzzified constraints instead of this strict equality. So with those prospects, I'd like to end my presentation, and thank you all for your attention.
Okay, thank you for a nice talk. Are there some questions from the audience? Comments, remarks? If maybe I have a short question. Okay, you propose some theoretical approach how to achieve, how to handle with mainly with subtractions. Or if I would be somebody who wants to use this approach in some applications, what shall I do? Because I mean those interval yes approaches had some expressions, and if in the case I would use them, then I would immediately get the result. What shall I do in this?
So in the use case of compositional data, we get back to the difference or the subtraction case.
Mm-hmm.
In case it's not the difference, that we get a general function. However, we can still use the framework of fuzzy variables because they are an interesting way to look at these quantities as being the value of a variable, which will yield comparable results. However, it will be slightly different formulas, of course, and maybe not. We won't necessarily get these nice characterizations.
Okay, thank you.
That's
some other questions? If not, so let's thank the speaker once more. And the next speaker is Petra Števuliakova. And the title of her talk is Relation in Complete Correlation and its application on interval operations.
Good morning. Thank you for the introduction. Um, I'd like to welcome you at my presentation. The title was already mentioned by Jirka. I want to add another comment that this work and this research is a joint work with my friend and colleague Zahra Alijani. Okay, let me start it. With Zahra, we are interested in interactivity relation because when we are dealing with some real applications where the fuzzy numbers or fuzzy sets are present, some real variables, then we need to take into account that these variables are not independent. They somehow interact to each other, and when we want to work with them, we need to take into account these interactions. But for example, traditional fuzzy arithmetic does not take these interactions into account usually. So we were interested in this field to explore how is it with some other operations and how we connected with some interactivity relation between fuzzy numbers and intervals. In this talk, I will speak about a particular case of interactivity. It's called complete correlation or linear interactivity. And I will introduce two operations, division and multiplication, which take into account this relation of complete correlation. Okay, I will start with the definition of complete correlation or linear interactivity. Okay, if we have two fuzzy numbers, or as was said, fuzzy intervals, we say that these two fuzzy numbers are completely correlated if there exists two real parameters, Q and R, such that these fuzzy numbers are joined by a particular case of fuzzy relation JC, such that the elements of the fuzzy numbers are connected by a line given by the parameters Q and R. And these parameters also derive if this correlation between fuzzy numbers is positive or negative. It depends on the parameter Q. If it's Q positive, then they are positively correlated. If it's Q negative, they are negatively correlated. Here is just simple illustrations of this correlation. So in both illustration, we see two fuzzy numbers, A and B, and in the middle, there is a fuzzy number representing the fuzzy relation J of complete correlation. And we see here is the line which connects the elements of the fuzzy numbers. In the first case, it's in positive way, and in the second case, it's in negative way. Okay, let me mention that this relation is directly connected with the notion of symmetry, because if two fuzzy numbers are symmetric, then if there exists a complete correlation relation between them, then it is also positive and also negative, this correlation, because the fuzzy numbers are symmetric. But in the case when the fuzzy numbers are non-symmetric, and if there exists a correlation between them, then it can be either positive or negative with respect to the shape of the fuzzy numbers. Okay, and now I would like to introduce how we can define or how we can work with fuzzy numbers which are correlated, completely correlated, or joined with some other interactivity relation. I will mention that interactivity and non-interactivity was originally introduced by Zadek, and then it was defined by joint possibility distribution, but I will not go into the details here. I will just mention that actually interactivity is defined in that way that if the relation J is equal to minimum T norm, then we say it is interactive. Otherwise, they are interactive, and it also says us that this fuzzy relation is always then less than or equal to the relation given by the minimum T norm, and the same holds for alpha cats. And for this fuzzy relation, which represents the interactivity relation, was defined as a so-called subject extension principle. It was somehow mentioned also by Jan before, that it's extension of the classical functions to fuzzy functions operated over fuzzy numbers which are joined by the fuzzy relation J, by the interactive relation. And then this extension is actually given by this formula, where we see that we operate over these elements which are really connected by the relation J. And of course, everybody can see, because it was also in the presentation, that if the fuzzy numbers are non-interactive, so this J is the minimum T norm, then this subject extension principle is actually Zadek's extension principle. Okay, I will just briefly mention the second theorem, and it says how we can work with alpha cats of this subject extension principle. So if we have the extended function, then we see that this property holds, and if the extension is a fuzzy number, we can directly obtain the infimum and supremum of these alpha cats given for these elements which are joined by the interactivity relation J. Okay, now I will move to the second part of my talk, which is our main work, which I will present, and it's how we can define two operations, division and multiplication, for completely correlated. I will now firstly start with intervals, real intervals, which are completely correlated, and then I will show you if and how is it possible to extend these operations to fuzzy numbers represented or defined by alpha cats. Okay, so we assume that we have two intervals A and B, which are completely correlated. So it means that there exists two parameters Q and R such that these intervals can be derived from each other by these two parameters and by the border elements of the interval. And then we can define the division of these two intervals we call JC division, which is actually derived from the subject extension principle, and it results in two intervals which are dependent on these parameters Q and R. Yeah, I forgot to mention that I was speaking about symmetry of fuzzy numbers and how is it connected with positive and negative correlation. And let me just mention that in the case of intervals, we can always assume that two intervals are positively and at the same time also negatively correlated with different couples of parameters Q and R. And these operations, divisions and multiplication, depends on these two intervals, and the results differ. Here in this table, I will show you how is the result influenced by these parameters, and I will explain it in the comparison with two other divisions. The first is generalized Fukuhara division, or for short G division, which is defined in this way. It's similar like the Fukuhara generalized subtraction. And the second one is Zarek-based division. And we could conclude that if we have two intervals which are completely correlated, and if they are both positive or both negative, and we assume the positive correlation between them, then the result is the same as the result of G division. And in the case when we assume the negative correlation, then the result is equal to the Zarek's division. And the opposite actually holds in the case when we have one interval is positive and one is negative. Then for for positive correlation is equal to Zarek, and negative correlation is equal to G division. And the third case is when we assume that 0 is contained in the interval B, then the result of JC division is in between them, actually are subintervals of each other. Here is just really simple examples. If we have two intervals, both are positive, and if we assume the positive correlation, then the division of these two intervals gives us this result, and is actually the same as result of G division. But if we assume the negative correlation between these two intervals, we obtain different result of the division, and it's the same like Zarek division. And another example is when we have a 0 inside of the interval B, then in the case of a positive correlation, the result gives this interval. The results of a JC division gives us this interval. In the case of negative correlation, we obtain these intervals as a result of JC division. And in comparison, we see what are the results of G division and Zarek division, and these two intervals are in between them, actually. It's are subintervals of the Zarek. Okay, how is it with multiplication? The situation is similar. We again have two intervals which are completely correlated, connected by the two parameters Q and R. And the multiplication of these two intervals results in interval which can be obtained by minimum and the maximum of this set. It's again dependent on the parameters Q, R, and the borders of the interval A. But there are exceptions. This result does not hold in all cases. Here are the exceptions. In particular case, for example, when we have two intervals which are both positive or negative, and for these particular parameters, we cannot derive one border of the interval directly from the borders of intervals A and B, because it's not such straightforward. We need to search for supremum. And again, the similar situation is when we assume these intervals, one is positive, one is negative. So it is possible to find it, but it's not straightforward given by the borders of the intervals. Again, it's dependent of the positive or negative correlation. So we have these cases in comparison with standard interval multiplication based on Zarich's extension principle. And again, in the case when the intervals are completely correlated, both are positive or both are negative. In the case of positive correlation, we obtain the same result as standard interval multiplication, but in the case of negative correlation, we obtain a subinterval of this one. And similarly for the other cases, which is quite similar to the previous table with division. Here again, the very short examples, two positive intervals, and in the case of positive or negative correlation, we obtain different results. One is equal to Zarech multiplication, and the second one is subinterval of this. And in the case of this example, where we have two negative intervals, again positive and negative correlation. So in the positive correlation, we obtain directly this interval, but in the case of negative correlation, there is the exception. Okay, I will need to be very fast. In this part, I want to mention how we can somehow introduce some interactive invertibility property between multiplication and division. And we actually obtained few results. It's again for the intervals. So the first is was quite straightforward, that this invertibility, this equivalence can hold in the case where this JC division gives us the same results as G division, and it's invertible with the classical multiplication of intervals. And it's very natural because this is actually the definition of G division. So this result was straightforward. Second result is how is it with JC multiplication and JC division. So we also obtained this result that there exists also complete correlation relation between these operands. So this equivalence is again preserved. This one is very short, and just for if it's possible to extend to fuzzy numbers via alpha cats. And let me say that in the case of division, it's easy. The definition, it's actually the same for alpha cats. But in the case of multiplication, it's not straightforward because there were these exceptions, and we cannot guarantee that it will be the proper fuzzy number. Okay, I will skip it. These
Okay.
are conclusions. Everything was said what I wanted to say.
Okay,
Thank
we
you.
need to finish this talk. So let's thank the speaker. And there is not enough time for a long question and long answer. So is there a short answer? Short question?
Sure. Answer.
Does anybody have a question? Okay, so maybe during the lunch. Okay, so let's thank the speaker once more. And the third speaker is Jelizaveta Lievinska. The title is Fuzzy Relation Aggregation Approach to Weighting Experts. Please take the floor.
Okay, hello everyone. My name is Jelizaveta, and today I'm going to talk about determining the weights of financial analysts' opinions using fuzzy relation aggregation. Okay, so we will start with some theory. So the fuzzy equivalence is a binary relation that is reflective, symmetric, and it holds T-transitivity. And if we want to aggregate many of equivalences, we still want the aggregated value to hold all the properties. So it should be reflexive, symmetric, and T-transitive. And we can do it in the following way. So if we consider a continuous and Archimedean T-norm that can be constructed using additive generator G, and if we have an aggregation, if we have aggregation operator H that is subadditive, then the aggregation operator A, if H is constructed this way, then this A will be T-transitive. From this theorem follows that if we take some subadditive function, in this case it is a weighted sum, then this A will be transitive. So this is aggregation operator, and it will, if we aggregate this way equivalences, then the result also will be equivalence because it will hold, because it will be reflexive, symmetric, and T-transitive. So yes, it's the continuation of a corollary. We got the way how to construct aggregation operator. We know the additive generator G. We know that there is this weighted sum function, but the problem here is weights, because how do we define them? How can we find them? Who tells us what they are? And how we can assign them? And I think this is a real problem, because in real life scenarios, it's pretty hard to determine these weights. And if we talk about expert systems, these weights are usually just taken from the air. It's just, okay, this expert is 2, this expert is 1. So the weights are the problem. And also with the weights, we can manipulate the results. And I think this is a problem because, because manipulation is the problem. Okay, and yes, my concern was, how do we know these weights, or how we can determine these weights? Because one way is just to ask experts what are the weights for this, but can we trust experts in mathematics when they are not mathematicians? I'm not sure. So we should have some possibility to know the weights mathematically. And now I will guide you through the financial example, because in finances we have a lot of data from which we can determine these weights. And now the example. So suppose we have an investor that wants to maximize the profit, and he is doing an operation with a stock every Monday. So every Monday he can buy, hold, or sell the stock. He has unlimited possibilities to do the operation every Monday, just with one stock. So for example, if he starts on Monday 0, he can straight in the row sell 100 stocks. So 100 for 100 Mondays. And just to say that this is like academic example, so we are not putting some limitations on how many stocks the investors hold, but he wants to do it every Monday. And looking retrospectively, he always knew what had to be done. So if the price went up compared to the previous Monday, then the stock had to be bought. If it went down, that it had to be sold. And if the price fluctuated a little bit, or there is no change, that then there is nothing had to be done the previous Monday. But our investor, he is super busy. So what he does, he listens to analysts. He listens only to free analysts. And every Monday, these analysts tell him what to do. So some says you need to buy, you need to sell, you need to hold. Unfortunately, the investor has only free analysts, so he can't take the mean of their decision, or he cannot take the majority because the majority is not always present. For example, as here, because everyone says its own opinion, or he cannot take the mean because the mean pretty often will just tend to halt operation because it's the safest. So he needs to somehow think how to find the ways how to trust these experts. So he needs to assign weights to the opinions of these analysts, and he can do it. So yes, he needs to assign the weights to these analysts, and then he needs to aggregate these opinions, these suggestions. And what he does, I mean, our investor knows equivalence relations. So what he does, he for every suggestion, he calculates the equivalence relation with the operation buy. So if the suggestion is to buy, then equivalence relation is equal to 1. If the suggestion is hold, then it's 2/3. And if suggestion is to sell, then the equivalence is 0.5. This is Hammacher equivalence with lambda parameter equals 0. I think we can take another, but it is easier to take lambda 0. So yes, again, he would, for example, here it would be 0.5 because it's the red one is to sell 0.5 equivalent, 0.5 equivalents, and the equivalence 0.5, and etc. And when we want to combine these equivalences, he uses the corresponding aggregation operator, which looks like this. So it is 1 divided by 1 plus weighted sum with analyst weight times the distance between the buy operation and the suggestion. And that would be the aggregated value. Yes. So, okay, we found out the way how the investor can aggregate these values, but the problem still is with weights. We saw that there are weights included, but how do we determine them? And pretty easily, because we know what should have been done. So we know that at some point the stock had to be sold, or it had to be held, or it had to be bought. And knowing this, we construct an optimization problem with the aggregated weights, and this way we find these weights for the corresponding analyst. Yes, sorry? Yes, based on the past, how many values we have in this case? We had 500 values in the past, and we took 400 of them to do optimization problem, and then 100 to test it, just to be sure. And I mean, since it is a popular stock, it was Apple stock, and we have a lot of data of it because it is in the stock market for a long time. Yes, and it just we minimize the square error between the real values that had to be made, the real suggestion, the real what had to be done, and what was suggested, and we obtain the following results. So using optimization technique, we calculated that the weight of the experts are as follows. And if we later plug in these values into the new test data, we have the good mean square error, which is approximately 13%, which means that our investor pretty well can maximize the profit. And here we see that the weight of the first analyst is the highest. So maybe we can trust him, but I didn't check if we can trust only him. What happens if we remove C and D analysts? So we need still to aggregate their values. And what I else want to stress that here, the value A suggestion corresponds to these values. So it shouldn't be always one. It should be, if the suggestion had to be hold, it should be 2/3. If the suggestion had to be sell, then it is 1/2. So we are not always optimizing to one. Yes, so this way we obtain these weights. What else would be interesting to look at? I think it would be interesting to look if we can find if some investors are better at some movements. So, for example, this investor is better at predicting when the stock will go up, or this investor is better when predicting when the stock will go down, or it will stay the same. And maybe for every, and then we could find the weights for every suggestion that the investor is, or sorry, not investor, but the analyst is doing. So yes, it is all. Thank you for your attention. And if you have any questions, I'm happy to answer.
So thank you for your talk. Are there some questions? Yes, Jan.
Yes. So thank you for your presentation. I had a question about your example, which the economics part. So when predicting which action to take, you have 3 actions: buy, sell, and hold. However, I had thought that hold is never the optimal action because even if the stock stays the same, the other ones are also have profit 0. So would it make sense to go to from 3 suggestions to actually a 2-action model? I only predict buy or sell.
So I understand the question. Thank you for it. I actually, I think that it makes sense to have hold operation because we have transactions fees when we do some buy or sell operations, and we have hold when the price moved not bigger than 2.5%. So maybe it's not, maybe the profit it's not worth to the fees.
Okay, thank you very much.
Questions? Irina, please.
Thank you. Yeah. Can you please once again explain the influence of similarity relations or equivalence relations, in solving this problem? Because finally you concentrated on selecting weights, right?
Yes.
Yeah, in order to have the aggregated mean. However, where is, the role of equivalence relations? Thank you.
So in that case, the equivalence relations was the aggregated equivalence relations was the ones that had weights. In this case, we switched from equivalence relations to more determining the weights of the experts. And to determine the weights of the experts, we need to have some functions that involves weights. And that's why we used fuzzy equivalence relations and later their aggregation. Depending on the question about symmetry and reflexivity, I'm not sure if I got it correct, but in this case, I doubt that I got it correct, but in this case, it really wouldn't make any difference if we switch the analyst suggestion and buy in the places. If we switched them, because here we would just have absolute values. That's all. So yeah, I'm not sure. You can correct me if you meant something different, because I didn't understand it. And reflexive, yes, the reflexivity, if we have operation by and operation by, then we have one. So it is there, but yes, maybe you can reformulate it, because I doubt that I got it. Yes. Yes. So we use Hammeher equivalence with lambda 0, and then the corresponding aggregation operator will look like this, because, sorry, because the inverse of the additive generator of the Hammeher T-norm will be at the end almost the same as the equivalence. So it's just a construction of the form. It's just, I think it's just coincidence that it turned out so nicely similar to that aggregation operator looks so nicely similar to the equivalence.
Okay, maybe I would stop the discussion and maybe you can continue during the lunch and after the lunch. Now it's time to, so let's thank the speaker once more. And it's time to start with the last talk of the session. The speaker is Špirkova Jana, and the title is Towards a Solver-Free Best Worst Method.
Okay, thank you. Ladies and gentlemen, I would like to talk about my recent work. So I concentrate on evaluation of sustainability pension index in a lot of countries, not only in Europe, but during whole world. And I worked with best worst method and other previous well-known methods. So in best worst method, I need a solver, because author of this best worst method is Jafar Rezai, and he prepared absolutely perfect free solver. But I wanted to extend a little bit this theory without using solver. So my title is Towards a Solver-Free Best Worst Method. I would like to only remind you some method on determining weights in multi-criteria decision making. You know, well-known Sati exact method, maybe Sati approximate method, and Thurston method of paired comparison. And the last one, already mentioned, best-worst method. Again, I only remind you some Rickert scale. You can see that some indicator, maybe criterion is extremely important. We put number 9, and consequently very strong, medium, and equal importance. We can use these numbers, and we can use also even numbers, not only these ones. And inverted values are this fraction. I would like to remind you exact Sati method, because you see that we need create whole matrix. In the rows, you can see individual indicators. Please observe here is a I1, I2, I8, and so on. So they are reordered with respect to importance. You can see also this situation that I put from 1 up to 9. And in this column and also in this row, you can see corresponding weights. So these numbers, you know, if I1, the importance is the same. And if I reordered these indicators with respect to importance. So I have from 1 to 9. And this problem is also calculated using solver, for example, in Excel, in other programs. And I am going to discuss about the best-worst method. This best-worst method is recently very popular because we need in calculation only one vector and the two vectors. In reality, two vectors, because I need to select the best indicator and the worst indicator, and then I have a vector the best to others, this one, and others to the worst is this one. So using the solver, I can evaluate weights, corresponding weights. And you see that I need solve minimax optimization problem. And Jafar Rezai implemented in his program all these inequalities, all these conditions. So it's very nice. You can see I would like to remind you this website because you can find here all information about best-worst method, and it's very nice because it's free solver, and you can also teach or learn this method. And this method, it's very popular because has a lot of citations. So, what is my idea in this problem? I wanted to determine weights by a little bit different problem, different way. I wanted to. The first idea was that I am going to apply my original study about the mixture functions. And mixture functions are weighted arithmetic means where weights are determined using function. So, but I only try to apply this formula without this xi in the product and also this one. I put originally only fx divided by sum of xai. And I didn't obtain suitable weights. So I only try to extend this formula like this one. And I try to calculate the weight with respect to this one. So you see from this formulation that weights needn't be monotone in general. So it's very easy because you know that once more, I only remind you, you see without any problem this simple formula for weights. X1 represents the rank, importance level. For example, our numbers from 1 to 9. And also, if I assume some function, this function controls how aggressively importance increase if rank. And this, you know, from our numerator, you see that is the raw weight from before normalization. So, you know, it's very easy because if I have this formula, it is enough to calculate partial derivatives with respect to each variable. And I only remind you that if I want to derive this formula with respect to each variable, I denote it an I and denominator S. And I would like to remind you that these partial derivatives, I must divide it on two possibilities. If k is equal to y, I have this one, in the numerator. If k is not equal I have in the numerator 0. So partial derivatives, it's very easy. For k equals 1 and for k is not equals I. And from this condition, I am able to determine some sufficient condition for possibility to be these criteria weights monotone. That's I can calculate without any problem. If I have some suitable function, so a little bit later I show you very elementary examples. But if I have if I already calculated weights, I need determine so-called consistency index. You know, I only remind you if indicator A is much more important than B and B is much important than C, you know that we expect that A should also be more important than C. So I am going to start with this fraction. And I need to determine, if I want to determine this consistency index, I need to determine best indicator with maximum and worst indicator with minimum of this simple expression. Let's define capital B, argument maxima of this expression, and W, argument minima from this one. And then if I determine this expression, it represents best values, best to others and others to the worst. So, and core idea, my determination of consistency index is this equality. Perfect consistency means if this equality holds, and then consistency index can be determined by this way. And also, maybe in this case, I need maybe some solver, but this solver I am able to create without any problem, without any special function in Excel. I am able to create only in some sheet in Excel. So if this consistency index is smaller than 0.1, it's all procedure suitable. And now I only show you some examples. If I use power function, and with respect to alpha, we have linear weighting. So for alpha equals to 0, we obtain Thurston method. And Thurston method is only created with numbers 0 and 1. If some indicator is most important and other one, I put 1. If not, 0. And for alpha equals to 1, quadratic thing, and if alpha is greater than 1, is strong dominant of top ranked indicator. So in not only in this moment, because I have only some examples, but we cannot say which function is bad or good, but which function is appropriate for some special case and comparison of indicators. Exponential function is given by this formula, and with respect to my conditions for beta greater than 0, the monotonicity conditions are satisfied. And also I tried to calculate with this linear function. For lambda equals 0, 0.5, and 1. And only for a small illustration, because I don't want to tell you now deeply the whole problem, only on illustration, comparison with best worst method. You can see, for example, I remind you, here is indicator, and on the vertical axis we have weight. For the most important indicator, you can see with respect to best worst method is this value of weight. And for orange on this level, this slope of this linear function, what is very similar, maybe different possibilities. But for me, it's very interesting that what is monotonicity of these weights for each cases. Best worst methods you can see by blue color. But very interesting are also not only the best criterion, but also others. And very interesting for me is the last indicator, maybe the least important indicator, because this indicator relates with ESG funds. And you know, we have in Europe some Green Deal, but any country doesn't hold any agreement from this deal from European Union. But it is enough, maybe is good that this indicator is here. Maybe if it has very small weights, whether I can put out this indicator, maybe calculate with this indicator. It's on expert with which work with these possibilities. And also I use on illustration exponential function, and you can see absolutely different possibilities that if I apply power function with small power, you can see that I a little bit the same. And if I apply with very, very high power, so again, the least importance indicator has very, very small weights. So it is on expert what will be preferred. And my this slide is last one. And I would like to tell you that I need calculate not only consistency index, but also consistency ratio, which is a little bit modification. So, and on this consistency ratio, I need a lot of random results, and I must study deeply to calculate consistency ratio. So that's all from my side. Thank you for your attention.
Okay, thank you once more for your talk. Are there some questions in the audience? Still have time? Okay, I still have 4 minutes, so we can wait. So maybe Bernard, may I get the microphone?
It's not directly related to your talk, but to the methods. So Sati's method has been criticized for many things that can go wrong, like reversal reference, if you put in an almost identical alternative, and many other phenomena that can occur. Is there a way that what you do could help to reduce those like bad aspects of Sati's methods?
Yes, I no. Bernard, at this moment, I am a little bit confused because I had prepared also comparison with SATI method, and I put out in the evening. So this my result, it's very, very similar with SATI method.
And problems that we have with Sati's method, like if you enter an alternative that is identical or almost identical to an existing one, you can have reversal of the preference of other alternatives, which may or not be like the way we reason. So is it a paradox or not? And does the best worst method help for that? Because I don't know it. I'm just curious.
The best worst method works absolutely perfect, but you need solver, and yes, I can program solver, but if you have something free, so I apply my data in solver of Jafar Rezai, but I am with this problem started maybe 1 month ago, and I want to continue. I will see.
Okay, thank you. So 3 minutes left. Okay, if there are no other questions, so let's thank the speaker once more. And this was the last talk of this session. Maybe I have one comment. This is a mathematical event, and it was nice to hear here that we are not sure that we can trust expert in mathematics if they're not mathematicians. So it would be nice to hear what physicists, for instance, mean in their events on mathematicians. Anyway, it's lunchtime, so enjoy the lunch and also the afternoon.